The p-n junction is one of the most important building blocks of a typical solar cell. In the next set of the videos, we will introduce the formation and the important properties of a p-n junction in terms of solar cell performance. The main focus in this video is on the depletion region in the p-n junction. Before we start to discuss the depletion region, let's first review the structure of a crystalline silicon solar cell. Here we can see the schematic picture of a crystalline silicon solar cell. At the junction between the p-type and n-type crystalline silicon regions, there is a so-called depletion region. Another depletion region is formed between the p-type and the heavily doped p-type silicon material. But for the rest of this video, we will focus on the depletion region at the p-n junction. So what is a depletion region? And what is depleted in this region? What is the function of depletion region in a solar cell? The learning objective of today's lecture is to understand some of new properties of p-n junction at thermal equilibrium. Besides, you will get to know what the depletion region is, how it is formed, and why there is an internal electric field in the depletion region. The internal electric field is the most important feature of the depletion region for solar cell operation. To begin, we first take a look at the isolated p-doped and n-doped silicon materials. We discussed doping of silicon in a previous video. Here, we represent the p-type and n-type silicon materials using a bonding model. We will use the bonding model to visualize what is going on when we put the p and n-type regions together. Before we get started, I should note that the bonding diagrams here are severely exaggerated. We will show more dopant atoms in the diagram than the normal concentration of dopants in the material is, in order to get a sense of what is happening. In reality, only 1 out of every 10,000 or 1 out of every million silicon atoms is replaced by a dopant atom. Let's start with p-type silicon. P-type silicon is doped with elements from group 3 in the periodic table, which act as electron acceptors. Boron is typically used as a dopant for p-type silicon. At room temperature, p-type silicon has a higher concentration of holes than electrons. These holes are mobile, and when they move from their host atom, they leave behind a negatively charged boron atom. We say that the boron atom is ionized because the charges of the mobile holes are compensated by the ionized boron atoms. The isolated p-type silicon material maintains charge neutrality. N-type silicon material is doped with group 5 elements that act as electron donors. Phosphorus is generally used as the dopant for n-type silicon. Phosphorus atoms have 5 valence electrons, from which 4 make bonds with neighboring silicon atoms. At room temperature, the 5th electron is liberated from the atom and becomes mobile in the silicon matrix. Just as with p-type materials, the phosphorus atoms become ionized when the electron leaves the host atom. However, in this case, the ionized atoms are positively charged. The charged phosphorus atoms are compensated by the mobile charge carriers, in this case electrons, and therefore the n-type material is charge neutral. To make a solar cell, we put a p-type silicon and n-type silicon materials together. This creates a p-n junction, which is also sometimes referred to as a metallurgical junction. So the question now is, what happens to the doped materials when we make this p-n junction. Let's put the neutral silicon atoms in background of the diagram so that we can focus on the dopant atoms, since that is where the action is. Now you see only mobile charge carriers and the fixed ionized doping atoms. To give you some numbers to feel what's going on at the p-n junction, first remember that silicon has 10 to the power of 22 atoms per cubic centimeter. In a standard crystalline silicon solar cell, p-type silicon has an acceptor concentration at around 10 to the power of 16 per cubic centimeter. We could also say that 1 in every million silicon atoms is replaced by a boron atom. If we assume all dopants are ionized, the concentration of mobile holes has the same value of 10 to the power of 16 per cubic centimeter. We calculate the electron concentration in the p-type crystalline silicon, which is around 10 to the power of 4 per cubic centimeter. N-type crystalline silicon, on the other hand, usually has a donor concentration of around 10 to the power of 18 per cubic centimeter. This means that 1 in every 10,000 silicon atoms is replaced by a phosphorus dopant atom. The electron concentration in the N-type silicon is then 10 to the power of 18 per cubic centimeter. We can easily calculate that concentration of the mobile holes in the N-type crystalline silicon, which is around 10 to the power of 2 per cubic centimeter. So we see that on one side we have a whole concentration of 10 to the power of 16 per cubic centimeter, and on the other side is 10 to the power of 2 per cubic centimeter. There is an enormous difference in the hole concentration and electron concentration between these two regions. So what is going to happen? Well, these charge carriers are mobile, so we can expect them to move around. Because of this enormous concentration gradient and the mobility of holes and electrons, holes will diffuse from the p-type to the n-type crystalline silicon, and electrons will diffuse from the n-type to the p-type crystalline silicon. The holes that move to the n-type region and the electrons that move to the p-type region will quickly recombine with each other. This results in a part of p-type region that is depleted of the holes from the boron dopants, and an n-type region that is depleted of the extra electrons from the phosphorus dopants. Since the ionized dopant atoms are fixed in the crystalline lattice and cannot move, their charge is not anymore compensated by the charge of mobile holes and electrons. This leads to electrostatic charge buildup in both the p-type and n-type silicon. In this plot, the Greek character ρ represents the space charge density. Since there is a depletion of holes in the p-type region, this part of the interface is negatively charged. And since there is a depletion of electrons in the n-type region, this part is positively charged. The amount of charge in the p-type region is proportional to the acceptor concentration there, Na. And the amount of positive charge in the n-type region is proportional to the donor concentration there, Nd. The region where there are no mobile carriers is called the depletion region. It is also sometimes referred to as the space charge region. Outside the depletion region, the electrical neutrality is still maintained, and we call these regions quasi-neutral regions. One good question you may be asking here is, why is there a stop to the depletion region? Why don't charges keep diffusing until the concentration of holes and electrons is equal throughout the device? To understand this, we must know that the buildup of charge in the depletion region causes an internal electric field that has the direction from the N-type to P-type silicon. The buildup of fixed charge in the depletion region is responsible for balancing the diffusing mobile charges, since the electric field pushes, or as we say, drift, charges in the opposite direction from the diffusion. This means that there is a point where the internal electric field will be strong enough to completely balance the diffusion of electrons and holes. Using the equations we learned in the video on charge carrier transport, we can calculate the diffusion and drift currents of holes and electrons. When the drift of electrons and holes will balance the diffusion, then we reach the thermal equilibrium condition where the net current is zero. This will define the width of the depletion region. To summarize, because of the concentration gradient of holes between the P-type and N-type regions, initially holes diffuse from the P-type to the N-type region, leaving negatively ionized doping atoms in the P-type region. As a consequence, there is a buildup of a negative electrostatic charge in the P-type region. The same goes for electrons. Electrons diffuse from the N-type to the P-type region, which leaves the positively ionized doping atoms in the N-type silicon. Hence, positive electrostatic charge builds up in the N-type region. The depletion region is formed at the p-n junction, where mobile carriers, electrons and holes are depleted. Because of the buildup of charges, there is an internal electric field in the depletion region. Outside the depletion region, there are quasi-neutral regions without any electric field. Due to the internal electric field in the depletion region, we have drift of electrons from the P-type region to the N-type region, and holes drift from the N-type in the opposite direction. At thermal equilibrium, diffusion current is compensated by the drift current, so the net current is zero. Now you understand what is going on in the depletion region at thermal equilibrium and how this region is formed. In next lecture, we will look in detail into the band diagram of the p-n junction at thermal equilibrium and explore how to calculate the thickness of a depletion region depending on the material properties of the P-type and N-type semiconductors that we use to form a p-n junction.